Good morning. I feel immense pleasure to be here for the course Aircraft Stability and Control. Today I am in lectures related to neutral point and static margin. In the previous classes we have discussed about the contribution of wing, contribution of tail and some other basics of aircraft stability. And today is very important lecture about neutral point and static margin of the aircraft. In this today's lecture overview, I will go with introduction. Then I will discuss about neutral point. It is called NP, stick fixed. Here I am talking about stick fixed only. Means we are not disturbing intentionally any of the control. All controls are free to move by aerodynamic forces. We are not making any intentional deflection of any control. And then I am going to talk about static margin, and that is also for stick fixed condition. So if I talk about the contribution of the wing, so we have discussed that the wing contribution is, if the aircraft is just I am making one wing like this, CG is here. So if this is the AC and this is the CG of the wing, so if like this, then it is moment CM in this direction and it is a negative, it is good. But in this case, CM naught will be also negative. So if I draw like this, CM versus alpha, the plot will go like this. So how to make, but I want for the static longitudinal stability, two conditions have to be met. That is, CM alpha should be less than 0 or negative, and CM naught should be greater than 0 or positive. If you see this plot for this wing, CM alpha is negative. CM alpha is negative, but CM naught is also negative. So this, we need something else to make this positive. So we use the tail. So if we make the tail, then the same plot will be like this. This is the CM, this is the alpha, and your plot will be like this. This is the CM alpha is less than 0, and this is the CM naught also greater than 0. And this greater than 0 is done by the contribution of the tail. So this is very important, that contribution of the wing is always not stable, but if you add the tail or if you add the canard, aircraft will be stable. That is why we use this system. Now I want to discuss about the new topic, which is the neutral point or NP. So this neutral point NP is that CG location at which CM alpha is equal to 0. So this is the definition of the neutral point. So neutral point is that center of gravity location at which CM alpha is equal to 0 or neutral. Okay, so you can see here that here we have the wing, the CG of the wing is here and AC of the wing is here. In this, if the CG and AC both are at the same point, then same alpha will be 0. Then this point is called the neutral point. So if this center of gravity is moving towards the AC and the CG and AC both are the coinciding, this is the CG and this is the AC and both are coinciding, then it becomes the neutral point. Okay, so how to find neutral point? we know that the Cm alpha is equal to Cl alpha W. Just now we have derived this. XCG by C bar minus XAC W by C bar, where XCG is the distance from leading edge to the center of gravity, and this AC is distance between the aerodynamic center and the center of gravity, minus neta VH CL alpha T, 1 minus d epsilon by d alpha is equal to 0. For this aircraft, to find the neutral point, by definition, Cm alpha should be 0. So, this equation we have to make 0. So, if we make the 0, then we will get here this XCG will become XNP, because CG has gone. CG and AC are same. So, in place of CG, we will write NP. So, XNP by C bar, this one, is equal to XAC by C bar minus Cm alpha Fs Cl alpha W plus neta VH Cl alpha W alpha T divided by Cl alpha W 1 minus d epsilon by d alpha. This same equation we have taken out this and made as a XNP. That is the difference. Now, so we have find out here that this neutral point is a XACW by C bar minus Cm alpha Fs. Normally this Fs we don't consider as of now. So Cm, this XAC W by C bar plus neta VH CL alpha T divided by CL alpha W 1 minus d epsilon by d alpha. So this is the equation for neutral point. This is the equation for the neutral point. Now we have to find out the static margin. So static margin is the difference between CG and the NP. Okay, so static margin, CG should not go behind the neutral point. So that CG location at which aircraft become neutral stable, it's not depend on the CG, but it depend upon the aerodynamic characteristics. Let us do some approximation. Here we have to see that CL alpha W is equal to CL alpha aircraft. So alpha W is equal to alpha AC. So dCm by d alpha, we have to differentiate this Cm with respect to alpha. So dCm by d alpha is equal to CL alpha W XCG by C bar minus XAC W by C bar plus Cm alpha Fs. So we can make it like this: dCm by d alpha and 1 by dCl by dCl by d alpha. So this become dCm by dCl. So in place of dCm by d alpha, we will write dCm by dCl is equal to XCG by C bar minus XAC by C bar plus Cm alpha Fs by Cl alpha W minus neta VH Cl alpha T by Cl W 1 minus d epsilon by d alpha. So now continuation of this dCm, here dCm by dCl is equal to XCG by C bar minus XAC by ACW by C bar minus Cm alpha Fs, Fs is fuselage, divided by Cl alpha W is a wing alpha angle, plus neta VH Cl alpha T divided by Cl alpha W 1 minus d epsilon by d alpha. So now dCm by dCl is equal to, so here is what? From here to here, this is the neutral point, x Np by C bar. So we will write here dCm by dCl is equal to x Cg by C bar minus x Np by C bar. So we have taken the minus here common, so this will become x Cg by C bar minus x Cg by C bar. So the difference between neutral point minus xCg is equal to called static margin. So this is the minus Sm. So static margin is equal to 5 to 10% we take. Means if the margin is between 5 to 10%, then aircraft will be stable. Okay, so NP should be always behind to CG. So we have to take, this is the xCG and this is the xNP, and this is called here static margin SM. Static margin is xNP minus xCG, and this value is 5 to 10% is acceptable limit. So here we got that dCm by dCl is equal to minus static margin. Let's say that it is minus 0.1 or it is a 10% of the chord. Okay, so here is this aircraft, L is and W, and here we can see that this is the CG is here and this is the NP and this is the 10% of the chord. And so here CMO of the aircraft is 0.06 and your slope of this is minus 0.1. So you can get the CL as CL is equal to 0.6 or alpha is equal to 0.6 radian. This you can convert to degree. Okay, so like this we can find out different values of the static margin, and this static margin is very important parameter to understand whether the aircraft is stable or not. If the this NP is behind the CG, it is stable, and how much more behind, it is more stable. I have taken this references, that HOUT TR, Introduction to Aircraft Flight Mechanics, then Flight Stability and Automatic Control by the Nelson, and the NPTEL lecture from IIT Kanpur. Thank you very much for this class. Hope this will give you the knowledge and you all will enjoy. Please see the video, like it and subscribe it. This will be very good to have a better understanding and to popularize the course. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.